21, if you start with nothing, it was one of the multiple choice questions, which is not a suggested appropriate action to mitigate the issue. And it was like none of those work, or like two of them did. If you start with multiple choice, it was question 22 about resource use. It was like, which one doesn't mitigate? And it's like, if you found an alternative supply, like that actually would help. Recycling, that actually would help too. Waste less, that would help too. Use less, that would help too. It was like, should have been like an all of the above question rather than that. I mean, yeah. All right, today our focus is renewable energy resources. We want to move from where we've been talking and discussing in terms of non-renewable energy resources and start to consider some of these resources that are more readily accessible and that solve a bunch of the problems that we associate with the pollution and the unsustainability aspects, the surfacing of the global carbon cycle for our fossil fuels and nuclear energy. And so that's what we're going to talk about today. I have a few different class questions for you to answer. We're going to start with exploring wind, solar, hydro, geothermal to a lesser extent in terms of renewable energy resources. What do they actually involve? Although we talked about some of the specifics of them already in class on Tuesday. Why are they good? And then we're also going to make that negative flip. Why don't we see a lot more of these renewable energy resources? What is the next hurdle that we need to overcome in order to be really widespread in terms of and then for the remainder of class, I want us to really focus on energy efficiency. And this is a place where we can make the greatest difference probably in terms of energy usage and the pollution that comes along with it, is by using less energy to begin with. So we're going to focus on electricity and transportation energy efficiency today. Those two kind of aspects, the big places where we utilize electricity here in the United States. And as we're going to see in the coming weeks, those are the two big sectors that kind of work together to make most of our carbon dioxide emissions, largely that come from fossil fuel generation, fossil fuel burning, either in transportation or electricity generation. All right, I think most of you didn't notice my thumbs are. All right, where we left off in class on Tuesday was we were talking about nuclear energy. And we had talked about the good things about nuclear energy. There's a tremendous energy density. It's the best in terms of energy that's available, which means that there's the most high-quality energy that we can get out. However, because of the problems that are on this particular slide, it turns out that nuclear energy has a low energy availability and a rather poor EROI, that ratio of energy output to energy input. It takes a lot of energy, not necessarily to run a nuclear power plant. It takes a fair amount of energy to get nuclear energy out of the ground, to get it concentrated enough to be usable as fissile material in a nuclear power plant. And it takes a tremendous amount of energy in order to store the radioactive waste that comes out of these power plants. Here in the United States, we don't have any set facility currently that will store our nuclear waste from our power plants or from our military bases. We have designated a place in the western United States to do so, and they take our waste, but they are not yet fully, completely set up to be the place. So we see still a lot of on-site storage of waste at many of our nuclear power plants. And the nuclear power plants that we have in the United States were built in the 1960s and 1970s. And that means that they're 35 to 40 years old, which is kind of the end of the life cycle of lots of these power plants. That's how long they were built to last. And so we see a fair amount of our nuclear power plants are at the end of their life cycle. They're starting to be ready to be shut down, or else they need to be upgraded in terms of technology and usefulness for us to continue to use them. And so nuclear power was this growing sector of our energy resource. And then we stopped building new power plants because we recognized that we didn't have a plan for the consequences for the end of life of these power plants. And the more that we built, even though it would help us move away from fossil fuels, it creates this waste problem. And the big problem is the radioactive waste that it produces. The uranium-238 and 235, those refer to different isotopes of their element uranium that are utilized in the fissile material. They have an extremely long half-life, And so this is the half-life of these two different materials. This is how long it takes for half the radioactivity to decay. And so we're talking about, in the uranium, like the rest of the life of the plant. Okay? It's dangerous in the interim while we are storing it. It has to be kept away from humans and other wildlife. It cannot be allowed to leak into the air, onto the land, or into the water. And we have containment devices that will last us, again, for this kind of 50 to 100 year period. And then what happens to the stuff? Then what are we going to do with it? That's a huge open question. Okay. There are a little bit of contaminated materials that are produced every day at these nuclear power plants. Likely radioactive kind of disposable outerwear that the workers have on that had to be taken care of. The original power plants, there was water that was mixed directly with the fission material, and so we would end up with some radioactive water that needed to be contained and disposed of properly. That's not how we build our power plants any longer. The water that's used in this entire kind of steam to turbine to generator process is entirely separated from the radioactive chamber. It runs around it, so that's how it gets heated. And all of that water is essentially available to us again, even though it has been through and in this radioactive, potentially radioactive environment. One of the big problems that's associated with this is that you have all this hot water that's generated, and it has to be cooled down again after it's steam, and that's what actually those big towers are, is the big cooling towers that recondense this water and send it back through the cycle to be heated up into steam. It also means that lots of times for these power plants, as well as fossil fuel burning power plants, we have this hot water that's released into the stream or the lake or the ocean right next to the power plant. That's that thermal pollution water problem that we talked about earlier in the semester. That's where it comes from, is this hot water that is generated during the electricity generation process. So that's the heat pollution problem. There's a little bit of carbon dioxide release, not in the actual electricity generation any longer, but in the production of the materials to go into the chambers, in transporting goods and materials to and from the site, in closing down the site. There's, of course, going to be fossil fuel burn in that process. And as I mentioned at the very end of class on Tuesday, one of the big concerns that we have today with our nuclear power plants is that they were built during the 1960s and the 1970s. We have a very different climate in terms of geopolitical issues that confront us today. That's very different than then. And so we have real concerns about the security of these sites and maintaining them so that they can't be broken into and stuff material can't be stolen. Also that people can't get into them and create an accident that would happen that would release radiation from the site into the surrounding environment. One of the other reasons that we have really slowed both in the United States and globally our building of nuclear power plants is the accidents that can happen. When there is a breach of the containment core, you release radioactivity into the environment in really high amounts that can be really dangerous to both the people, the workers there, as well as the people living around the sites, and of course the ecosystem that's there. That has only happened in a very, very few instances where it has a full containment breach of a nuclear power plant, resulting in radiation release. The most famous of that is Chernobyl, and then the Fukushima power plant in Japan after their earthquakes and really phenomenal tsunami that came afterward. In those instances, it has been enough to globally scare us from continuing to build nuclear power plants, again, because we don't know how to deal with the fallout in a responsible fashion. Chernobyl is just now, like 35, 40 years after the actual Chernobyl event. I was like, oh my gosh, how old am I? That's like how many years ago it was. They're just now starting to open up some of the zones and say, hey, it's actually safe enough for people to move back into their homes. There are actual communities that were asked to leave in the Chernobyl site that never did, and they have lived there this entire time, and they're just now, opening up roads and being able to get easy access back with their communities around them. The scientists say that the Chernobyl site itself is really a beautiful Russian prairie land today, and that because humans have left the area, has reverted to a lot of its natural state, and that overall radiation levels are low except at the actual site of the Chernobyl power plant itself.
Like three-eyed animals and new species?
Not yet. And I think that has been something a little bit interesting, is that maybe some of these genetic mutations that we anticipated for this type of fallout have not come to be, or that if they happened, they were still in the womb, both to people and to organisms. And so those mutations got out I wanted to make sure our civilization would not be where it is today without fossil fuels, without nuclear energy. The electricity and the transportation opportunities that it provides have, I mean, honest to God, changed the face of the planet and the way that we interact with each other and with our ecosystems, greatly to the benefit of humanity. We have more technology, we have more education, we have better healthcare, we have more agricultural productivity because of fossil fuels and nuclear energy. But our use of them today is that fourth generation of the popcorn bag that we saw on Tuesday. Like, we are at the point where our use of them is unsustainable. And that in every generation that we use fossil fuels, we keep pushing the consequences of their use off to the next generation. And it's time for that bill to come due, particularly in the area of climate change. And that after 150, 175 years of burning fossil fuels more and more every year, we have built up enough carbon dioxide in the atmosphere to experience climate change and to be experiencing real ocean acidification. And I have ocean acidification in blue here because we talked about it in first semester. It's a lowering of the pH of ocean water that affects the organisms at their very base of the oceanic food web in terms of access to carbonate ions to build their calcium carbonate shells and skeletons. And we're not going to talk about ocean acidification in any greater detail this semester, but we're going to talk about all these other guys. Climate change in a couple weeks. We talked about pollution. We talked about habitat destruction. All of that comes with our use of fossil fuels and nuclear energy. And so if we want to avoid these problems, and we want to start to mitigate the problems, then we have to pivot from fossil fuels into something else, into renewable. Okay? The other thing that I want to bring home to you is that the use of fossil fuels in particular is problematic for human health. Okay? It releases particulates into the atmosphere that cause cancers, that contribute to respiratory illnesses. The habitat degradation and the pollution that comes along with it not only impacts organisms, it impacts us as well. And so even if you're not on the climate change like bandwagon space shuttle, okay, let's think about what we want this vessel to be these days. Then I want you to recognize from the aspect of human health that moving to renewable energies is something that benefits society, that there aren't any, there are very few negatives to the move to renewable energy. It has a higher net energy, has a higher EROI, in some cases has a much better energy density, and it's much more sustainable. So, if we want to define renewable energies, there is a kind of the opposite of our non-renewable energy resources. Our renewable energy resources are ones that are naturally replenished on a human timescale. So because of solar energy, in most cases, constantly being present on the Earth's surface, we have the heating and cooling differentially of air masses that produces wind energy. We have actual light photons that are constantly streaming down on the surface of the Earth. That's the basis of solar energy. Because we have the heating of water on the Earth's surface, it evaporates and precipitates down somewhere else and collects on the surface of the Earth, and it runs and flows back to the ocean. That's hydroelectric energy. Okay? All of these things can be tied back to the sun, which is this phenomenal resource that's not going to run out anytime soon. Okay? Yes, eventually the sun will grow into a red giant and consume the Earth, but by that time, it's not going to matter if we're using renewable or fossil fuel energy. All of these things are replenished and are constantly re-available. We don't have to wait hundreds of millions of years for them to ferment inside the Earth in order to be available to us. The other thing that's very, very important in renewable energy resources is that they do not short-circuit the global carbon cycle. The production of energy, either transportation or electricity, from any of these resources does not release excess carbon dioxide into the atmosphere. It does not take carbon dioxide that is stored in the ground and then suddenly pump it into the atmosphere. It takes carbon dioxide that's present here on the surface and might burn it in terms of a fossil fuel, but that's carbon dioxide we already have up here. Okay, that's carbon dioxide that's already part of our current atmospheric concentration and our current short-term global carbon cycle. It's not taking stuff that was in the long-term global carbon cycle in terms of coal, which petroleum or natural gas and suddenly injecting it into our current kind of surface global carbon cycle. Again, we talked about these a couple weeks ago before spring break. What does fall into the category of renewable energies? Wind, solar, hydro, biomass production. We'll talk a little bit about biofuels today, geothermal. The map here shows you in darker, intense colors a higher availability of these different possible renewable energy resources here in the United States. So different areas are rich in different renewable energy resources, just like richnesses in mineral resources as well. Particularly, look like the western United States again is really good for generating renewable energy. One thing we haven't talked about that I hope that you'll get to today is to recognize that wherever we're making electricity in particular, it then has to be distributed to the people that are actually going to use it. And so part of energy efficiency, part of switching our electrical generation process is making sure that we have availability, reliability, distribution capacity in our electricity generation that matches what we have today in our fossil fuels. Okay, anything that surprises you?
I was just thinking about the western United States. I used to drive out west on a regular basis, and you hit like Wyoming,
Yeah.
and it's all just the windmills everywhere. In fact, it looks like the aliens are invading at night because there's little red lights.
Oh yeah, and even if you go from here to Chicago, you'll drive through the windmill farms, and we'll talk about solar first, but then we'll get to wind. You drive through the windmill farms, and at night there are all these blinking lights in unison, and there's like half of them that's not like. I kind of like it. I don't know why. Yeah, maybe it's like Christmas.
Yeah.
Okay, we're going to talk about solar energy first. Okay, how do we get it? Most of the solar energy that we produce is through the use of photovoltaic cells. There is a diagram of one here, and essentially what happens is that we have our light photons that are coming in from the sun. They hit a molecule that's in a film at the surface of the photovoltaic cell, and that adds energy to that particular molecule. Okay, that molecule then moves through a fluid and donates its energy in the terms of electrons to another compound that's in the bottom of the photovoltaic cell. And that movement of electrons is electricity. And it's over and over again. Usually the best types of compounds to use for this, they're regenerative. So once that particular molecule has grabbed on a photon of light and it's donated its electron off, it's ready to grab another photon of light and can be reused over and over again. The key here is that that electricity that's being generated by this movement of electrons has to be stored in a battery so that then we can get access to it. Okay. The battery helps us then to have stored energy for use overnight when there's not a big rain of photons coming in because we're turned away from the sun for some hours of the day. Okay. And so a lot of photovoltaic battery cells and movement into solar energy has focused around not only perfecting the different types of compounds for efficient transfer of energy from photons into electricity, but then how to store this in a reasonable fashion, how to get it stored in batteries that hang on to that charge, that last for a long time, that feed out the electricity in a very reliable and steady fashion when necessary. And so there's these two technologies that have to work together in order for photovoltaic to work really well. You have to have the actual photovoltaic cell, and then you have to have a good battery that comes along. Stuff that's often used today is we have these thin silicon wafers that are part of this photon absorbing and then electron moving process that makes now silicon one of these desirable minerals that we're trying to mine out of the Earth's surface. There's also a variety of different metal ions that are useful in this process that now have become very important and prosperous in terms of mineral extraction that we weren't interested in before until we started to push into photovoltaic cells. We might be more familiar again with these big fields of solar panels in order to generate lots of electricity. Again, you see them every once in a while as you're driving alongside of the road. This can be small scale as well, and that's what I want to kind of remind you of, is that for each of these renewable technologies, you can do it massive, and you can try to fuel a community. Or you can think about it on a more individual scale. What can I do for my city block? What can I do at my house? In Florida, I've probably mentioned this, my in-laws heat their pool with a solar voltaic cell that's on the roof. So on sunny days, the pool is really hot. On cloudy days, when you really want to get in the warm pool, it's cold. Right, that's how it works. This happens to be a Walmart in Puerto Rico that runs all of its electricity off the solar cells that are on it. Another few examples, again, here's one of those big fields of solar panels for electricity generation. Notice that it works best in desert ecosystems or in grassland ecosystems where there's not trees that can shade out the solar voltaic cells. That can be problematic. You also remember it needs to be up high, again, so building shadows don't shade over the solar voltaic cells. As we move into developing nations, one of the big pushes of the industrialized nations is to say to these communities, don't even start with fossil fuel electricity generation. Let's start using a renewable energy technology because that's going to be so much more sustainable for your community. And so single solar panels like this, small wind, small hydroelectric in individual communities can give them that battery and electricity generation that they need to run the lights in a few businesses, to recharge cell phones, to have internet access for a few hours of the day. And sometimes that's all that a community needs in order to get going economically, to be able to sustain itself. And so small scale renewable is really big in the developing world as well. All right. There are a couple other uses of solar power. We think of it in terms of electricity generation, but I also want you to recognize that solar energy can be used for heating. And you can do this now, particularly in the spring, when we're starting to get longer days and we're getting sunny days. You can utilize passive solar heating, the sun's rays to directly warm a space or a material. This means opening your blinds on the sunny side of your house so that your heater doesn't have to run as long on spring days when we have these kind of cold mornings but warm afternoons. We can take advantage of passive solar heating in order to do a little bit more, and that we could put water in a heater on a reservoir on the roof of a building, and it can absorb heat from the sun's rays, and then you can pump that warm water throughout the house to be water or to be a source of heating for your home. And that's one way of, again, kind of taking a chunk out of what's usually natural gas and transforming it into a renewable energy heating source. Active solar heating happens when we do that using the sun's energy to warm a fluid that's utilized in the house either immediately or later for this heating process or as your hot water reservoir. This technology is available and it works pretty well in certain locations where it's going to be sunny a lot of the time, when you know that you may have low hot water use in a particular household, and you can account for this. This is a technology that definitely isn't like large scale yet. Where we're like, oh yeah, we're totally going to replace all natural gas water heaters with active or passive solar heating. Okay, you're not there yet, and it probably wouldn't work for the demand rate in which we require hot water in lots of our households and in businesses and in commercial settings. Okay, but it can help. It can be another aspect to building or environmentally wise water. All right. The other solar system that I mentioned on Tuesday is solar thermal heating. And this is what's shown in these particular pictures. It's usually done with curved mirrors that look very much like solar panels. And the curved mirrors reflect the sun's rays back to a single point, usually a tower, looks very much like a lighthouse. And the concentration of that solar energy then is used to evaporate water that's in that tower into steam, and then that steam turns a turbine that runs a generator to make electricity. Okay, that's solar thermal. That's using the same kind of technology based for a fossil fuel burning power plant, but instead of burning a fossil fuel to do that steam production, we're going to use solar energy to do it instead.
Is that so expensive?
It can be,
Because I think about the cost of mirrors in general.
Yes, exactly. And so if you think about transitioning a fossil fuel power plant into solar thermal, you've got to buy all of these mirrors. You have to have them perfectly aligned. They have to be perfectly made in order to have the right angles for the sun, you have to have a system that's gonna move the mirrors as the sun moves through the sky during the day, so that you're constantly producing steam, so that you have a constant electricity generation. So again, the technology is there, but we see it usually on very small scale, and in very specific areas, again, usually very arid environments, where there's lots of sunlight, and that's the kind of climate that's in that particular. Okay. When we think about the problems with solar, we have solved a lot of the thin film cell technology. We've come a long way with solar batteries in the last 30 years. We've solved those problems. I would say our big problems to date with solar, and why we don't see it as a greater portion of our renewable energy resources, is because of its reliability. You must have sun in order for it to work in any of its aspects, whether it's the heating aspect, whether it's photovoltaic cells, whether it's solar thermal. And so when you have cloudy days, when it rains in particular environments, you don't get reliable electricity or heating production. And that means that it can't fully replace fossil fuels, because you have to have that backup system in place for when you don't get enough sun. There is technology now that is attempting to move into UV radiation, which is present all of the time, even through the cloud layer, in order to replace our reliance upon actual visible light photons in this technology. And that's something that boosts the reliability, it boosts the usefulness of this particular renewable. The other big problem, of course, is materials cost. It is expensive to make this technology, and that has always kind of priced it out of the market in terms of renewables. It's just now, as we've seen manufacturing processes in Asia turn to photovoltaic cell production, that we've gotten cheap photovoltaic cells that has kind of boosted the usefulness again and the profitability of solar energy. What we're seeing, of course, today is that as our trade policies with Asia change, we're trying to restart the U.S. manufacturing process for these types of solar cells, so that the money that goes into starting this as a renewable is something that's funding jobs and manufacturing here in the United States as well. But that's more expensive. Okay. And scalability then is the final thing that comes with this. If you're worried about reliability, you're less likely to put in a lot of money to build solar. Without a bunch of people buying solar, the price remains high for solar production, and that affects scalability. It's kind of this never-ending cycle of it costs a lot, so nobody's going to do it a lot, which means it continues to cost a lot, which means you can't scale it up. Some really kind of innovative uses of solar, of course, are things like this electric car charging station that is in France. The idea that if we want to move away from fossil fuels and transportation, we need to move to electric cars. So then we need that electricity to be generated from renewable energy rather than from a fossil fuel power electricity plant. So these types of uses of solar can really target a specific need, and they can provide it in locations where it's going to be most useful, right? Like you can put solar panels up kind of anywhere, and they can provide for these uses. Does anybody have solar cells on their house?
No, the neighbor behind me has like their entire roof on.
Oh, that's cool. It was kind of common in Seattle to see the houses' roofs, if they were in the right alignment, to have these solar cells on. There's one house in our neighborhood that does it. The zoo, just a couple years ago, covered their parking lot, right? Which was like, yay, a covered parking lot. My car doesn't heat up, and it can get to my car when it's not raining. And then they put solar cells on the top of the parking lot, which is so awesome, on the parking lot roof. And so they generate a ton of electricity that provides for their own needs, and they probably do excess that they can sell back into the electricity. And again, those types of options for solar are starting to gain a lot of traction, where you do it small scale and enough people do it in kind of a co-op situation, you can provide for your own needs, and then you have excess that you can sell back into the system. All right. Wind energy then is quite different from solar electricity generation, and again, we use wind just like solar almost exclusively for electricity generation. There are always those solar-powered cars in the kind of car design manufacturing, but they really haven't taken off, because you have to cover your car with solar cells to be able to drive it, and then again, you can only use it on sunny days, and then it's very so we don't see any solar or wind-powered cars kind of out there.
That's compounded.
Okay, so for wind, we're using blowing air in order to immediately turn the turbine to fuel a generator to make electricity. And so there's no burning, there's no water usage. And so it really helps us on water pollution. There's almost no CO2 generation other than in the manufacturing of these turbines and in their maintenance. When they break, you gotta fix them. If you want to take one down, I've never really seen one taken down and kind of wasted. Of course, there's going to be some CO2 associated with that as well. The ones that make the big wind farms are enormous. Okay, like the ones in the picture here. We see them being set up offshore in this particular picture. Generally, they have 3 to 4 blades on them in the most modern designs. They tend to be oriented to the dominant wind blowing direction of a region. And in a particular wind farm, you'll see them kind of at slight angles to each other so that they don't block the wind from nearby turbines. And they can take advantage of it. Something's always moving in the field, kind of whatever day there is, all right? So again, there are different regions of the world that are better adapted for generating wind renewable energy electricity. If it's calm where you are, like it's not gonna work, okay? On the plains of Montana, across the plains of the United States, offshore, we have onshore, offshore winds every day, great wind generation, constant, consistent wind in order to power these turbines. Places where I lived in Alabama, not so much, okay? You guys, looks like we finished lunch. Angry Bird Tower building over here. All right, so that's big wind, and that's generally what we think of in terms of wind. Again, the batteries are really important to be able to store the electricity that's generated. And then notice that you then have to send it on into the electric grid in order for it to be useful. So you have to have some time. In terms of what's useful for wind, it's really widely available. In 2013, which was a long time ago, it provided like 3.5% of global electricity. I think it's gone up to something closer to 5 to 7% today. Wind has been one area where we've seen a lot of growth in renewable energy. It's grown a lot faster in recent years than has solar. It seems to be something that people more readily understand the process of electricity generation. We've been using turbines and wind energy in terms of windmills to do work for us for a long time when it comes to human civilization. Potentially, here in the U.S., we could do all of our electricity from wind alone. If we really went hard into wind and said we want to transform our electricity economy, we can do it. We have the wind availability, we have the technology that we can switch fully to this particular renewable. It has a really, 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 really high net energy production and an extraordinarily high EROI. It's one of the best in terms of energy efficiency. There's not a lot of energy loss. There's only a few types of energy transfer that have to be made in order to go from the wind blowing across the surface of the earth to electricity generation, and that really helps its efficiency. It has a relatively low cost to build and maintain. Again, the materials and the startup costs can be quite high, but then it tends to pay for itself on the order of 7 to 10 years. It has relatively low habitat disturbance. So again, you can think of solar. If you want to do a big solar voltaic cell field, you've got to take a field of habitat and turn it into solar cells. That doesn't happen with wind. You have a small imprint of the turbine, and then it's up off the ground, and it's not interfering with the ecosystem that's at the bottom. Pretty low greenhouse gas emissions. Again, the actual generation of electricity does not produce any excess carbon dioxide. And it is projected to have an enormous job creation capacity, that there could be 400,000 jobs in the tech sector in order to build and maintain these devices and then to kind of run the electricity and electricity distribution that comes from them. And these jobs pay pretty well. Like we're talking like $64,000 to $75,000 a year to be a windmill engineer. That's kind of cool. I'm not cool with the heights, but.
Oh, I didn't even notice someone standing in there.
Yeah, I feel like this would be a career choice for me if I had like a different like track. And maybe I'd get used to that. Okay. What's the problem with wind? Big problems, not as much as with solar, but there is problems with reliability, in that the wind has to blow in order for the turbine to turn to make electricity. So we tend to try to site our wind farms in reasonable locations that are gonna produce reliable electricity. And that means that, again, certain communities are gonna be better set up for wind than others. You have to be able to adapt to the changing wind patterns, how that might change with climate change, and then to be able to store when you have excess, so that in times when there's low wind production, you have the battery capacity to provide for the community. You can't have a blackout or a brownout just because the wind isn't blowing and it's a cloudy day. Okay, like what happens if you have wind and solar to provide for each other, but then you get those calm, cloudy days? Like, what are you going to do? You have to have batteries or something else to provide for the community in that case. At the university I taught at in Seattle, they had wanted to move to their own electricity production, and they had put up some solar cells, and they really wanted to do micro wind. They wanted to have a couple little turbines on some of the buildings. But they were on the side of a hill in this little valley in Seattle where it was never wind. And the wind engineer said, it will never work. You will never make electricity if you put this up. So it didn't make sense to go put it up in that particular location. There is a problem in that birds and bats occasionally run into the turbines, and then that's it. Okay, like if you hit one, it's over for you. It can be really problematic in some locations. We think about 800,000 animals a year die from interactions with wind turbine blades. This means that we have to begin to be smart about where we place wind farms. And that you shouldn't put it on a migration route for waterfowl in the United States. You'll kill a bunch of ducks. Okay, like that's not cool. In California, they realized they had a real problem with their endangered bat population. The bat's echolocation was telling them that the whirling, twirling little tip of the turbine was they wanted to. And so they would fly right into it on purpose.
So if you're trying to get rid of
Which was
bats,
bad. Right, like if you want to get rid of bats, which we don't in the United States to the greatest extent. So, again, you have to be cognizant of the ecosystem in which we're trying to do this and generate wind. Yeah. What are they going to do with that? Oh, they have changed, in some cases they can change the blades so they look different to the bats, and that helps of course. The other thing is you gotta take them down, you gotta go with something else that there aren't bats. The best solution. There can be noise that's generated with this. Some communities really complain about a high-pitched noise that causes headaches and nausea in some residents. There's really conflicting scientific evidence about that, whether or not it's true or not. Definitely for people that suffer from this type of interaction with wind turbines, it's real for them. There are lots of communities that fight the placement of wind because of the disruption of the skyline, and they say that they moved to the beach, they moved to this particular location in part for the view, and then if you're going to put up a wind turbine, it changes, of course, the landscape in terms of our aesthetics. As I said, I kind of like wind turbines. To me, they're like a sign of a future. They're a sign of hope, and that we're making real change in our communities for renewable energy. I don't mind them when I go to the beach and I see them offshore. I'm like, look, what a great community that's investing in renewable energy. But there are communities that have been able to move wind generation away from them because of the tourism aesthetic aspect. So you have to keep in mind that location for people as well as for wildlife. How many of you have driven by a big wind farm? Yeah. And that's something that, think about that. That's new to our generation, to be able to see big wind available and actually producing electricity. Yeah, I'll let you know.
How far can the electricity that the wind turbine produce reach? For the communities that don't want them, is it still possible for them to use
Yes, it is. For every distance that you move, it costs more to get it back to you. And remember that as electricity is traveling down in these power lines, there's some electricity lost due to friction with the molecules. And so you reduce efficiency, which is why the cost gets greater to bring the same amount to you, the further away you are from the generation site. And so that's the aspect, is that you can move it farther away from you, but then you'll get less profit from it because you lose some as you transfer it to you. Willow.
How much on a good day would one wind turbine produce?
I think it really varies. I have to look for sure. I always kind of assumed the big ones here were the 10 kilowatt ones that we talked about as far as energy density. They come, I think the next slide is there's little wind too, and there's Yeah, you can do micro wind where you have these little individual wind turbines that do less. It's all about the generator that you're running. You know, what is the capacity of the generator that you've attached to the lines. Okay. It doesn't have to be big wind. It can be small wind. These things cost, you know, from $4,000 to $70,000, again, depending upon the size of the turbine that you're installing. This is a community in England where each new house gets its own little micro wind turbine that is attached to it that helps provide some of the home electricity, and then of course goes back into the community. Whether or not you can do small wind, again, is really, really location dependent. You have to have the right wind to have a kind of an average wind speed that's required in order to be able to produce it in a productive fashion. So just like you can do small solar, you can do small wind too. Yeah.
How long do they last?
Oh, that's a great question. I would say that these wind turbines are built to last between 50 and 75 years. They need regular maintenance, just like any, you know, kind of motor. They need, you know, there's lubricants and fluids that have to be replaced. You gotta clean them. The turbines, so you know, themselves are clean and they don't get weighed down with a bunch of gunk, and that makes them spin more slowly because they have more weight they have to turn. But that's my understanding is 50 to 75 years. Are you okay? Okay. The next one here is geothermal. Geothermal is when we use heat that's stored in the Earth's crust and mantle in order to heat fluid, and then or cool it. Kind of depends upon what the temperature is outside in relation to the ground that we're flowing through. And we can use that heated or cooled fluid then directly in heating and cooling purposes within a home or a business, an individual house. And in some cases, in terms of geothermal electric production, again, we pipe water down into the hot earth. It gets evaporated into steam, and then you go right into the electricity generation process. And that's what we do for geothermal electricity production. So you can do it in terms of what we see here, which is a geothermal heat pump, where it's used on a home scale in order to heat and cool water, or you can do it for electricity generation. Yeah.
The Sustainability Committee here at UC Claremont
Yeah.
is working on, UC Claremont is going to switch over to geothermal. Very soon they're getting bids for it to be the first green campus on UC.
Ooh, that's super cool. I totally want to do this at our house. Like, I feel like if my husband is like, okay, I'm like, okay, the next thing is, let's try a geothermal heat pump, right? It's like a big deal. My parents have this at their house in Minnesota, and they have this big field that runs out in the back of their house, so they have all these pipes that are down in the ground, 10 to 15 feet, and the water in it gets cool. During summertime, they blow air over that cool water in the pipes, and that's air conditioning. In wintertime, it's warmer underground than it is in the house, and they do the opposite. The hot water comes in, they blow air over it, and that's their heat for the house.
Is that similar to like the swamp coolers you'll have out west?
Yes, very much so. Again, where you put something in the ground, kind of like a cellar, right? Put something in the ground to be cool, and then it stays at temperature year round. You know, so even when it's freezing outside, it's actually warmer down there in the cellar than it is outside. The cool thing about my parents' house is that in the wintertime, I mentioned this to you guys, when the pull on the electric grid is really high to produce heating for other homes, the power company says, okay, we're turning off our distribution of heat to your home because we know you can make your own heat. And in that way, they can save and help the entire community by their own heat production at their own house. All right. Here's the geothermal electricity production. Here we're having heat that's stored in the Earth's crust or mantle. We pump water down, it gets evaporated into steam, and then we can make electricity like we would in a fossil fuel power plant. Again, geothermal is something that has a high net energy, high energy efficiency, but it is very, very location dependent. You have to be next to hot springs. You have to be near a volcanic region in order to have the right geology for geothermal electric production. Almost anybody can do a geothermal heat pump in their home, given the right kind of rock formations underground that is, you can dig down there and not unstabilize your house, destabilize your house, right? But electricity production is much more scattered. Yeah, Willa.
What like habitat destruction or environmental?
I would say in this case for electricity production, it's similar to, I would say like solar thermal. We're going to have some footprint of the electric power plant itself. But other than that, it's very little. These are regions where there's a very specific and endemic type of, usually microbial life in these hot, acidic, or alkaline regions. There's not a lot of other stuff that's out there to be disturbed. And the addition of water doesn't radically change the system in these locations. There's a footprint to mining it, putting the pipes in the ground, setting it up. But after that, it's pretty minimal. Okay. All right. Hopefully, the last one here. Oh, geothermal. Again, the big disadvantage of geothermal is the scarcity of the suitable sites. So we have to have the right location to do geothermal. Here, I might note that chapter 16 in our textbook has all these pros and cons of all these different renewable energy resources with these different guys. What I'm likely to ask you on an exam is, I'll say, pick 2 of these 3 renewable energy resources. Tell me why they're great. Tell me why we don't use them for more of our electricity generation. Be aware of what the advantages and disadvantages are for each of these. Look for the slide, and then also don't worry about copying everything. Okay, all right, last one here is hydroelectric. Hydroelectric is similar to wind in that we're going to use flowing water now instead of air in order to turn the blades of a turbine to make electricity. And so here we have moving water that's going to turn the blades of a turbine to run a generator to make electricity. It provides already close to 20% of our global electricity needs. And in some locations where there's lots of hydroelectric available, it does 90 to 95% of the electricity generation for big swaths of regions. Again, though, it's very location dependent. You have to have flowing water in order for it to work. Okay? And again, you have to have a distribution system for that electricity generation. Like wind, it has a really high net energy and EROI, very efficient. No short-circuiting of the global carbon cycle. There's no actual CO2 generation in the actual electricity production. It's pretty low cost. Usually these types of installations are in association with a dam that we place over a river stream. We get the advantages of the reservoir behind it, frozen irrigation, freshwater drinking reservoir, fishing. There are problems, of course, with any dam as it comes to changing freshwater flow and temperatures and migration of organisms through the freshwater ecosystem. But adding hydroelectric to an existing dam or building a dam with the usefulness of hydroelectric added in helps in some of those cases when we know we're including environmental habitat destruction. We have to do kind of anyways for either irrigation or drinking purposes. Very low greenhouse gas emissions when it's done in temperate ecosystems. In tropical ecosystems, the reservoirs behind the hydroelectric dams, they tend to go into anaerobic composition of organic matter and they make methane. And those reservoirs in tropical locations release a lot of that more potent greenhouse gas methane. So again, that reservoir production kind of pluses and minuses associated with it, just like we talked about the pluses and minuses. That's all built in baked into hydroelectric. Okay. All right. So the big problems, as I mentioned, with hydroelectric are the ecosystem damage that comes with its production, and that you inherently are altering the ecosystem when you build a dam with hydroelectric built in. Even though you get this great sustainable renewable energy resource out of it, the habitat destruction is some of the worst for renewables. Definitely we have problems with reduced flow downstream, and flooding can happen both behind us when we build the reservoir and then downstream in certain situations when we have extreme precipitation events or when we have damage. Another big problem comes in that the slowdown of water in the reservoir behind the dam causes siltation, increases the chances of eutrophication in that ecosystem, where we're allowing pollutants like nitrogen and phosphorus to build up in that reservoir. As I mentioned, we get methane release due to the anaerobic decomposition of organic matter in reservoirs in tropical locations. And then again, it's very location dependent. The largest hydroelectric dam in the United States is the Grand Coulee Dam in Washington, which is the smaller little picture that we have here. Produces all of the energy almost for the entire state of Washington as well as parts of Idaho. It's a phenomenal resource. However, it's this enormous concrete structure that has completely changed that local ecosystem. The two pictures that we see here are satellite images of the Yangtze River before and after the Three Gorges Dam was built. The bottom picture is before, like the opposite of how we normally do these things. The bottom picture is before, and then the top picture is after. And one thing to notice is you can see this big reservoir and the flooding of water that happened all the way up the river valley. One of the problems that this particular system had is that the flooding took out a bunch of vegetation. And then because there weren't plants, the hillsides destabilized, and then we had a bunch of mudslides. And that added a whole bunch of sediment to the water, which has turned it that kind of glacier silt till color to it. It's like that kind of bluish green now instead of blue. It also meant, because we had all these mudslides, that it was harder for vegetation to regrow on the hillsides, and they continue to have flooding and mudslides throughout the river valley as a result of the building of this reservoir, the flooding that happened behind the dam production. Any questions about hydroelectric? You can do it small, or you can do it big. If we think about doing hydroelectric in an environmentally responsible fashion, we want to do it small hydro. Here it's eco hydro in terms of like super small versus micro hydro. In these cases, you have a device like this one where you take part of the stream flow and you divert the water for a short distance to turn a turbine to run a generator, and then you dump the water right back into the stream. You don't actually build a dam. You let the stream keep flowing, and you take a little bit of the water for a moment to generate electricity, and then you send it on. This allows the ecosystem to remain largely intact. You're not building a true dam. You are diverting some of the stream flow, though, for some time period. The problem is you can't do this large scale, right? If you want to generate a lot of electricity with hydro, you have to build a dam. You have to generate that reliable flow of water. And so run-of-stream, run-of-mill hydroelectric can really help again in particular communities, but it will never be of the scale size necessary to do a large chunk of renewable electricity production. This particular one, I think they said it costs about $50. You can build, again, these types of small hydroelectric in a big, 50-gallon oil drum in terms of having a small turbine that turns water out of the barrel and then out of the water. Okay, any questions about renewables? We've done the pros and cons of all these different guys. You got an idea of how they all kind of work. Yeah, Dominic.
Is it pretty equally used globally, or other, like, are we the leader of renewable energy use?
Our mix here in the U.S. is mostly hydro wind with a smaller bit of geothermal and solar. It's a very similar in Europe, and so European countries and the EU have gone pretty hard into renewables, largely because they don't have the big fossil fuel deposits that other nations do, and so they're really dependent upon imports of fossil fuels. So part of their safety and security as a nation was to get energy independent, and it has this added benefit of like making them, CO2 neutral in the shorter term. They do mostly wind. They have less hydro, although it's part of their mix. And have more solar than we do. Again, based upon the climate and the topography and availability of what they have. Wind is a much bigger part. Yeah.
I don't know if you said earlier, but can we use wind energy like on a home scale, like you can some of the others?
On a which scale?
On a home scale. like
Yes,
just
you definitely
your
can.
house.
And my current reading of the literature is that the suggestion is like, you wanna get off the grid. You wanna have your own home with running water and hot water and stuff that, you know, separated from the commercial electric grid. That you should have solar cells and a wind turbine. And if you have it available to you, you can have one of these run-of-stream hydroelectric yourself. Usually when we think about small hydro, it's on the scale of 4 to 5 homes that are gonna share a small grid. But it's a combo of some solar cells and a small turbine that can give you home energy. Okay. So the last type of renewable that I want you to think about just a little bit is biofuels, okay? And so this is gonna start us into a little bit of getting you to chat to each other rather than me just talking to you today. Everybody get the worksheet today? And I'm gonna ask you to answer the first question on the worksheet. And in a second here, I'm gonna give you a card. And you are gonna find the people who are in your group to talk to about this based upon what shape is in the middle of that card. Did everybody get one? Okay. All right, so there's a shape in the middle of your card. This one is a D with a bunch of squiggles in it. Okay, there's like stars and rectangles and other things. Okay, so grab a pencil, stand up, okay, and come up to me and grab a card. Okay, and then find the people that have the same shape